Hello everyone. So before we get started, you might want to get out your lab notebook as well as your big map because you're going to be wanting to jot down some notes as we go over this. So make sure you have those out. If you need to pause and get yourself all set up, go ahead and do that now. Before we get started, I just wanted to review a couple of important things with you. So first of all, we want to remind ourselves that the Earth is made up of a lithosphere, that rigid upper part of the crust that's broken up into pieces called plates. And these plates float on top of the kind of molten, liquid-like layer called the asthenosphere. We also want to remember that a plate boundary is where two plates meet, and a fault is any crack that occurs in the Earth's crust. Right? So anytime you see blue during this, you might want to write that information down, something important. Right? We want to remember that all plate boundaries are faults, but not all faults are at plate boundaries. An example of this would be the Ramapo Faults that caused the earthquake of 1884 that we talked about in class. Right? So the Ramapo Fault occurs in the middle of the North American plate. So it's a fault, but it does not occur at a plate boundary. Unlike the San Andreas Fault, right, that is both a fault and also occurs at a plate boundary. Alright, at this point you might want to pause the video so that you can copy this table down into your notebook. You can title the page Plate Boundaries, Faults, and Stresses Notes. And you might want to turn the page sideways so that you can fit the whole table on there. I'll give you a second. Go ahead and pause the video to make sure you can do that. Alright, the first thing I wanted to do was just review transform boundaries. Right? We talked about transform boundaries when we talked about the San Andreas Fault in California. A transform boundary is when two plates are sliding past each other in opposite directions, right? This is also called a strike-slip fault, and you experience shearing stress at a transform boundary. Right? So the stress that is experienced is called shearing. So go ahead and update your table. The first row you want to fill in. You can pause the video if you need time to do that. The next plate boundary I wanted to talk about was divergent plate boundary, like the mid-Atlantic ridge that we talked about. So at a divergent plate boundary, two plates are moving in opposite directions. You can kind of help yourself remember this by thinking of the word divide. When you divide something, you're splitting it in half, you're separating it. So divergent are two plates separating, moving away. And as you can see here, as they separate, magma is pushed up from below, and it replaces that area that's left in the middle, cools, and becomes new land. So it's not that there's a big hole that's left in the earth. There's constantly new land that's coming up, cooling, and creating newer crust. Right. So when this happens in the ocean, we get a mid-ocean ridge, and it's this long, mountainous region of volcanic activity. I'm going to show you a clip right now of something called pillow lava. Right. And this is lava that's coming up under the ocean. This is underwater. And it cools very quickly, the surface of it. You can see the dark part is the cooler lava. And inside you can still see the very superheated lava. Eventually, this will all cool into new oceanic crust. So that's the process that creates the mid-ocean ridge, like the one in the Atlantic. Now, when this process happens on land, like it does in Iceland, right, we have a divergent boundary cutting Iceland in half, it creates something called a rift valley. And you can actually go to Iceland, the Icelandic Rift Valley, and you can walk between the plates. You can see the North American plate on one side and the Eurasian plate on the other. And you can see that this new land has just been created by magma that's come up from the surface and cooled. So you can actually walk in between the plates at a rift valley. Another famous rift valley might be the Great African Rift Valley, you might have heard of. That also occurs there. And at a divergent plate boundary, we call that a normal fault. So whenever there's diverging plates, it's referred to as a normal fault. The type of stress that's occurring there is called tension. That's a pulling stress. So go ahead and update that row in your table. You might want to pause the video so that you can do that. The next type of boundary we're going to talk about is a convergent boundary. And that's when two plates are coming together. They're converging. Now there's really three scenarios at a convergent boundary. You can have two pieces of oceanic crust coming together at the edges of a plate. You can have oceanic and continental crust coming together, and you can have continental crust coming together. And depending on what type of crust is converging, you're going to get different things happening at this location. So we call this a reverse fault at a convergent boundary when two pieces of the plate are coming together. It's a reverse fault. And the type of stress that's being experienced is compression, a pressing stress. So these two pieces of crust are being pushed together, compressed. All right, so let's first take a look at a convergent plate boundary where two pieces of oceanic crust are being pressed together. We call it O plus O, oceanic plus oceanic. All right, so when an oceanic crust converges on an oceanic crust, the older oceanic crust is denser, and that's the one that will subduct or be pushed underneath. Right, and when this happens in the middle of the ocean, right, you've got oceanic crust on this side, oceanic crust on this side, the older crust subducts underneath, and that rock that's being pushed under heats the lower that it gets into the mantle, begins to melt, and a lot of gas and a lot of pressure builds. And eventually that magma is going to be pushed up to the surface. It's going to create an underwater volcano. And that underwater volcano, over time, will build up an island arc. And that's why we see lots of island arcs forming at these locations. One example of which would be the Caribbean island arc, right, which formed from the subduction of the older, denser oceanic crust of the North and South American plates underneath the younger Caribbean plate. Right, so you can see here it's subducting underneath, it's causing melting of rock, a volcano forms, and the Caribbean islands are built up over time. Another example would be the Japanese island arc. And the Japanese island arc is formed when the older, denser oceanic crust from the Pacific and the Philippine plate are subducting underneath the Eurasian plate. And that's what built up the Japanese island arc. And you can see there's also a trench forming as it subducts underneath. Right. Another example of an island arc would be the Indonesian island arc. Right? And you can see the older Indo-Australian plate is subducting underneath the Eurasian plate to form this chain of islands known as the Indonesian islands. And then finally we have our Aleutian island arc over by Alaska. It's a chain of islands that juts off of Alaska, and it's from the older Pacific Ocean crust subducting underneath the younger North American ocean crust. And you can see also a trench is formed here as well. All right, so I want you guys to pause for a moment and take out your big map, and I'd like you to star the 4 island arcs that we just mentioned. Find them on your map. Find the Caribbean, the Japanese, the Indonesian, and the Aleutian Island arcs. And I just want you to put a star next to all of them. And down in your key, have that star represent island arcs formed from subduction. All right, so take a moment, you can pause the video, go ahead and star those 4 island arcs on your big map. Once you've starred those, go ahead and update the table in your notebook. All right, we want to fill in compression, stress, reverse fault, the direction of the plates they come together, and then our examples of the different island arcs that form because of this happening. And you can pause the video to update that as well. All right, the next scenario is when oceanic crust and continental crust come together. And when this happens, oceanic crust is much denser than continental crust, so the oceanic crust is going to be the crust that subducts every time. So when this happens, we're going to get volcanic mountain ranges that occur along coastlines. They're not going to be out in the middle of the ocean like with the island arcs. They're going to be right on the coastline of a continent. So our biggest example would be the Nazca Plate subducting underneath the South American plate, creating the Andes Mountains, this chain of mountains that occurs all along the side of South America. And you can see the same thing happens with subduction. The rock melts, creates this hot magma that starts rising, creating a volcano, and you get a mountain chain that happens to be along a continent. Right. The other example, which we talked about in class, would be the Juan de Fuca Plate subducting underneath the North American plate to create the Cascade Mountain Range. That's a mountain range that extends from Washington down to Northern California. So at this point, you might want to pause the video and add to your map the convergent subduction area on the side of South America where the Nazca Plate subducts underneath South America. So you can add that as a subduction convergent boundary. All right, go ahead and do that now. All right, then you're going to update your table, and you're going to add the examples of volcanic mountain ranges that occur along coastlines, the Andes and the Cascades, to your table. You notice we still have the same type of stress, the same type of fault, and same direction of movement, because it's still a convergent boundary. It's just one that has oceanic and continental crust this time. All right, pause the video if you need to update now. All right, our final example, the convergent plate boundary where continental crust meets continental crust. When this happens, both continental crusts are not dense enough to subduct. So neither of them is dense enough that they can be pushed under. So what happens is instead is something called uplift. They both press upwards and fold upwards. And this creates mountains. Mountains that are not volcanic. They're just regular mountain ranges. Right? And the best example would be the Himalayas. And that's when the Indian-Australian plate crashed into the Eurasian plate and created uplift, this Himalayan mountain chain here. Right? And this is just kind of over time how the Indian plate crashed into the Eurasian plate. So this is how we get the Himalayan mountains today. So go ahead and take a minute to draw the Himalayan mountains on your map. Just label them Himalayan mountains. And you can actually label them C plus C for continental plus continental convergent boundary. And finally, you're going to update your table. Again, same compression, reverse faults, still coming together, but your example will be the Himalayan mountains this time, a mountain range that is not volcanic. All right. If at any point you missed something and you need to go back, go ahead and do that now. Thank you for your time, guys. I'll see you tomorrow.